Hey there, calc folks, back here with what is a third video in our study of multivariable functions here. We've introduced ourselves to them, the concept of a multivariable function, the domain, the range, beginning to illustrate vector valued functions multivariable, stuck in that old stuff. Multivariable functions, being able to sketch them out in terms of traces and level curves and their assembly into these three-dimensional surfaces. What we are going to look at, and then we followed that up with limits, right? We looked at a study of limits of multivariable functions and saw some of the intricacies there. The biggest one being that when we approach that independent value in our argument of the limit, as our independent value behaves in a certain manner, that behavior can happen really in an infinite number of different ways, as opposed to what we saw for single variable functions, right? And that does change the game a bit there, and does make it a bit of a trickier calculation overall in the end. Right? So, with the introduction of limits into these ideas, the idea of a multivariable function, what we're able to do, a lot like what we did back in Calculus 1, is we're able to use the limit to define an understanding of derivative for multivariable functions, right? And if we keep in mind what derivatives told us back with the single variable case, and if I flip over and bring some of this back into view, right? What we understood for the single variable case was that derivatives told us rate of change, instantaneous rate of change in our dependent value and the output of our function with respect to a change on the input, right? Typically, when calculated, interpreted as x, the input variable is increasing, and what would be the instantaneous change in y? Is it instantly going up by so much, or is it instantly coming down by so much? At instantaneous rate of change, right? The instantaneous rate of change in y with respect to a change in x. And we understood that instantaneous rate of change, right, graphically all corresponded to a slope of a tangent line, right? A slope of a tangent line to our curve f at some point of x equal to a on that curve would be given by the value f prime of a, right? We'd be able to take the derivative function, evaluate it at some value of x. We might say x equal to a, and f prime at a would correspond to the slope of this tangent line, right? This was the topic that we studied back in Chapter 3 of Calculus 1, right? And I shouldn't date myself with chapters there, but we spent two good chapters studying calculus, right, or the idea of derivatives back in Calc 1. We were introduced to them in one chapter. We were studying their application in the following chapter, right? What chapters those happen to fall in, I don't want to date with this video. So just take note. Go back and think about Calc 1. We did study derivatives for an entire chapter, and we did study application for an entire chapter. All right. What we're now coming back to is this idea of derivative in the multivariable context. Now, if you remember back in Calc 1, our study of the derivative, right, involved looking at a limit calculation where we looked at the behavior for and this all related back to the slope of the tangent line, right? We calculated the slope of the tangent line by examining the behavior for the slope of the secant line. How we examined instantaneous rate of change in y with respect to x back in Calc 1 involved an analysis of behavior for the average rate of change in our function, right? The average rate of change in our function y with respect to a change in some interval of x, right? With respect to a change in x over some interval of x, from x equal to a to x equal to b. Looking at that average rate of change over that interval, we were able to apply a limit and examine that behavior as that average as those 2 points on that average rate of change curve approached each other. As those 2 points on that average rate of change curve approached each other, right, at one point or the other, what you ended up calculating was the slope of the tangent line on that curve. All right. That limit behavior described the slope of the tangent line in that scenario. Well, we're going to see a similar idea here with multivariable functions. Except we got one issue. If we put 2 points on the curve, and I should be careful there, we're going analogous now to three-dimensional space. So if I put 2 points on a surface, right, and have one point approach another point, right, on that surface, right? Let's say I really should set it up maybe this way. Let's put a defined point on that surface. Let's look at the average rate of change in the surface right here, right? And if I look at the average rate of change in the surface right here, I can approach that point on my surface from any given direction. So I could actually analyze an average rate of change at that point in an infinite number of different ways. Which means in terms of any given point on our surface, there is an infinite number of different instantaneous rates of change in the output of the function at that point, depending upon, right, our approach on that point. Some approaches on points, right, produce no change, whereas some approaches of points will produce certainly great and positive change, whereas some approaches on points will produce perhaps great and negative changes, right? So there's an infinite number of ways to pass through a point. And that leads to an infinite number of ways to examine instantaneous rate of change, right? Unlike what we saw in the case for single variable functions here. And I do take note of that secondly here, right? Note in the case of the multivariable function, the rate of change in z depends upon the change in two independent variables x and y in the xy plane. And this change in x and y can occur in any given infinite direction in our two-dimensional space. All right? That change can happen in any infinite direction, folks. When we put ourselves at one point on our surface, and we are interested in what's going to be the change in the output of our function while passing through that point, well, there's an infinite number of ways to pass through that point. We can pass through in any different direction, right? We can analyze any average rate of change behavior from that point to some other point on that surface where there's an infinite number of average rates of change we could consider, depending upon direction. Right? As for finding the rate of change in z with respect to a change in x and y in the xy plane, we can calculate what's known as a directional derivative. All right? In terms of calculating any of these infinite rate of changes in x and y, well, I should changes in z with respect to a change in x and y in the xy plane, we could go about calculating what's known as a directional derivative, right? A directional derivative will tell us the rate of change at a point on our surface moving through any direction at that point. That's going to be given to us by what we call a directional derivative. This is actually a topic for some application of what we're going to develop in this section, though. right? Because in order to calculate a directional derivative, we're going to need two specific derivatives, derivatives that happen in two very specific directions, right, known as our partial derivative calculations. All right, so that's what we begin setting up here in terms of derivative calculations. In order to begin examining derivative at a point on a surface moving through in any given direction, in order to begin looking at what we're going to find is a directional derivative, right, we're going to need to rely on the calculation of two very specific derivatives for that surface, known as the partial derivatives of that surface. And what we're going to find is there's going to be a partial derivative with respect to x, the independent variable x, and there's going to be a partial derivative with respect to our independent variable y. All right. And those two partial derivatives can be used to find the derivative at, well, any of the infinite derivatives that we might be able to calculate with a directional derivative. All right. So I do make note of that in the following here, right? The directional derivative of f will describe the rate of change in z and any directional change in f's domain. To calculate the directional derivative requires the calculation of two other specific derivatives. We can perform with the multivariable function z equal to f of x comma y. The derivative is known as the partials of z, right? Or the partial derivatives of f, right? Respectively. And that is what I define as follows. And you're going to see a definition for this that looks very similar to definitions we saw defined back in Calculus 1. You'll see down here, folks, this is the definition for what's known as the partial derivative of f with respect to x, right? It does have its respective notation. Take note, that is the first thing we take note on here, is how do we see this symbolized in our work, what's known as a partial derivative versus what we might now define as a full derivative, a derivative that we calculated back in Calc 1, right? Which I highlighted above here, right? This might be denoted as a full derivative, and we see notation similar to this full derivative notation, except there are some changes. To begin with, you don't have really the use of primes anymore, folks. Prime is not as descriptive as it needs to be, right? So replacing the prime notation, we have what you see here is the subscript notation, right? The partial of z equal to f of x comma y with respect to x is either going to be z sub x, or you might see f sub x, or what you will notice is this will often be a function of x and y, so it'll be f sub x at x comma y. Very similar to how we interpret y prime and f prime of x, except the sub x highlights that it's a partial with respect to x, right? The other bit of notation we have relates back to this notation. That is what? Leibniz notation, right? That fractional notation, fractions of differentials. This is the differential change in y with respect to the differential change in x, or it's the differential change with respect to x for function f of x. All right? We see a very similar notation with respect to partials and the partial with respect to x. This notation seen here. Except notice the change. To highlight partial derivative in this notation, folks, to not confuse it with a full derivative, we use the Greek symbol del, right? Versus the lowercase del, versus d. It's an incomplete d, we might think. It's only a partial d we're illustrating here. We're going around it up, but we're not dropping back down to complete that d. We're making a partial derivative here, folks. This is the partial of z with respect to x, or we might say here is the partial, right, with respect to x for function f of x comma y. Right? That is z's partial with respect to x, or what we're going to later learn is first partial. This is f's first partial with respect to x. Notation, folks. That is all notation there. Right. Whereas this is how we define it. This is how we define that first partial with respect to x. And it should look really familiar. Right? It should look really familiar. It was very similar to how we defined this statement up here. And in fact, if I wanted to, I could probably add a line up here. Excuse me. And take note of what all this means. This is all just a limit. A limit as h heads to 0 for the quantity given by f of x plus h minus f of x all divided by h. If we go back to our understanding, right, for what was the derivative of f with respect to x, our full derivative of y equals f of x, it was understood this way. This limit is h heads to 0 for f of x plus h minus f of x all over this quantity of h. And what we were examining here again, folks, remember, was average rate of change. Average rate of change in some point on our curve at x and some point on our curve a little distance away from x. That point at x, right? A point at f of x plus h. And what we're doing in the limit is we're making this point that's a little distance away. How far away? H units away. Right? We're making it closer and closer and closer. We're making that distance between them head to 0, which is becoming our average rate of change, or becoming our instantaneous rate of change by examining the limit of this average rate of change. All right? Notice we see something very similar here. In fact, notice the only difference is this inclusion of y as an extra independent variable in that definition. Otherwise, that's the exact same thing as what I just typed above, except the inclusion of those two y's. All right, those two y's as independent variables in the multivariable function f of x comma y, where here it's being, the x is being evaluated at x plus h, but y is being left alone, right? Minus f at x comma y, where what you will notice is we are looking at change, average rate of change, but only where the x value is changing, right? The y value is not changing. And if y is not changing, what does that imply? Well, that implies y is constant in value. And that is going to be one of our strategies of approach for calculating these partial derivatives, is holding that y as a constant value and only considering the change with respect to x when calculating a partial of f with respect to x. We see a very similar definition given for the first partial of f with respect to y. Right? Except where there is a change, well, first of all, notice the notational change. With respect to y, in what's comparable to prime notation, we use a subscript y. This is z's partial with respect to y, or f's partial with respect to y at x comma y, because it's always going to be a function of x and y. So there's a little notation involving that relationship back to being a function of x and y, related to function f, but it's first partial with respect to y because of this subscript notation. Right? And then over here is our Leibniz notation. This is the partial of z with respect to y, or the partial with respect to y of function f of x comma y. This is a bit more of an operator notation. All right. In terms of how we define this, notice the difference. The only difference is instead of having x change in our average rate of change calculation here, we're strictly going to make y change. All right? We're going to look at a change on this surface where only y is going to be allowed to change. X, in this case, is not going to change. It's going to be held constant in our calculation. All right. Partial rate of changes and their respective definitions. Now, if we scroll down and I bring this into picture, I do try to help give you some visualization on your curve here. And give you a little description of that visualization. What do I say here? The first partials is z equal to f of x comma y, z of x and z of y. What do they describe? Well, they describe the rate of change in z with respect to only a change in x or only a change in y respectively. We've highlighted that up above. This partial highlights only a change in y respectively. X is held constant. At x comma y equal to a comma b in the domain of f, the value of the first partial of z with respect to x at a comma b, f's first partial of x with respect to x at a comma b, describes the rate of change in z equal to f of xy at that coordinate in the domain a comma b, where y is held constant at b and x is going to be allowed to change. Where z of y, right, z sub y, the first partial of z with respect to y, f's partial with respect to y at a comma b, describes the change in our function f of x comma y at a comma b, where x is held constant at x equal to a and y is allowed to change. And then I say, note the following illustration. All right. Note this illustration here, folks. What we see in this illustration is a point on our surface. Where again, if we go back to how all this opened, folks, there are an infinite number of ways to pass through that point on that surface. Think about, for instance, being an ant or being a person shrunk down and being allowed to walk around on top of that surface. Right? You can walk wherever you want on that surface, folks. But if at times you may want to pass through that point on your journey as you walk around on that surface. And when I say pass through that point, walking around on that surface, you can actually pass through that point in any infinite direction. You could pass from that point coming down here from this lower corner moving up to this right corner over here. Or maybe you're coming down from this lower corner here and passing up through the surface here. Or maybe you're meandering around and passing through that point on a circular path. Right? Or maybe you're down here and you're just kind of come up and pass through there. Right? On some quadratic path. Right? There's an infinite number of paths all passing through, right, that location on our surface. When those paths pass through that location on our surface, how quickly the surface's height is changing, how quickly this vertical measurement z, let's notice x and y, describe our orientation in the horizontal plane of this surface, y along this axis, x along this axis, whereas z describes the vertical extent of this surface. So as I'm passing through that point, I am changing my x and y values in a certain manner. And every different direction has x and y changing their values in a different way. Right? And respectively, z is changing with regards to how x and y is changing as we pass through that point. Right? So the change in z will not always be the same with every single different change that we could have as an observation for a change in those coordinates of x and y. That z could change very differently depending upon how we pass through that point. So there's really an infinite number of rates of change with regards to passing through this point. And we could calculate any one of those using what we call a directional derivative. We could calculate the directional derivative for passing through the point in this direction, or we could calculate the directional derivative for passing through the point in this direction, or we could calculate directional derivatives for passing through that point in the direction I highlight with this path that I denote in green, if you can see that color green, folks. Or I could pass through that point moving through this direction along this line that's colored blue, if you can see that color blue, folks. Right? But we could be passing across this surface through that point on one of these two paths. Where notice what's happening on one of these two paths. To begin with, if I'm moving along the green path, the path that starts here, travels up through that point, and ends over here on this portion of the surface. Right? Or I should say, along that path, y is being held at a constant value. If we were actually to project that path down to the y-axis, and I maybe should have put this in the illustration, but I didn't want to jumble up the illustration with too much material. But if I was to translate that path, drop it down to just the xy plane, it would be a horizontal path passing through just the value of y. Whereas, well, the value of x then, x would be any given value along the number line here. From this location on that line to this location on that line. X is going to be allowed to change while y is being held constant. This green path is highlighting the path we would travel on to calculate our partial derivative of z with respect to just x changing. Similarly, along this blue path, if we were to translate that down to the xy plane, that would be strictly a path in the xy plane, right? Where x would be held constant at the value of a in our illustration here, y being held at b, x being held at a. This is the coordinate at a comma b, we might say. Right? X would be held constant at a, and if as we moved along that path, we would be moving along that line in our xy plane that would be held constant at a, where y would be allowed to change from this location along the y-axis to this location along our y-axis over that interval of values of y. And that would have us changing solely with respect to a change in y. X being held constant at the value of a. So what the green path and the blue path illustrate on this surface are the two paths we would move along to pass through that point, right, and have an average rate of change in our surface given by either the partial of z with respect to x or the partial of y with respect to z. All right. Now, I do think I say that down below here. Let me scroll down. scroll back up, and I'll just dip out of the picture for a minute and let you take this all in. That is the end. If need be, you can always pause the video here and take in some of that. All right, folks. We're not going to spend a lot of time reading back through this. This does say what I said above. Right? You can certainly read through that, and that all just comments on, again, what I said above here. And I've already spent 30 minutes on the theory here. I would probably like to get down and get into some calculation for you real quick. One thing I will point out, though, just to close out with here with respect to the theory, is notice we didn't really talk about tangent line. And that's because there's really an infinite number of different tangent lines all at that point. Right? There's a tangent line for each and every one of those paths passing through that point. Right? Just depending upon what direction we head through. There's a tangent line in the direction here of the first partial with respect to x, and there's a tangent line in this direction here. Right? And there's a tangent line in any direction we want that we pass through that point. In fact, if you put all those tangent lines together, you end up with a description of what we call a tangent plane. There's actually a tangent plane tangent to the curve at this point. Right? We're going to talk about tangent plane also here, folks, and the first partials are going to play a role in that calculation. Where there would be tangent lines in our illustration is if we highlighted or just examined the cross sections in any given direction. Then the partials would correspond to the full derivatives for the curves described by those cross sections. All right. So a little bit more in also into the direction that we're heading there, folks. But what we want to see is some calculation. And to begin with respect to calculation, you can always rely on the limit definition. All right. I wouldn't encourage you to rely on the limit definition. I would begin to understand that every calculation we perform in the background is being calculated as a limit definition, right, using the limit definition, but is being calculated in the background using the limit definition in the form of our fundamental derivative rules, or in just all of our derivative rules that we understand for derivatives that we developed back in Calculus 1. Right? But we're going to treat y as a constant. Right? I wouldn't encourage doing this each and every time, folks, but I want to show you that that is where, right, what we're going to see develops from. All of the derivatives we calculate, all the partial derivatives we calculate, are grounded in their definition. Right? But we're not necessarily going to always use this definition in our approach to that calculation. Right? So, consider applying the above definition, right? What definition are we referring to? Is that limit definition. This definition seen up here. Define, first of all, the partial of f with respect to x. I think I leave off the y because it's a very similar method. But I just look at, let's calculate this. Right? Much like we would have done very early in Calculus 1, right? When we were first introduced to the derivative. We would have calculated its value for a couple simple functions using the defined value, the limits value, which is going to require some application of limits. Right? But here we're applying a single variable limit, right, to this calculation. Or we'll see how this all plays out. All right, certainly. Note for f of x comma y equal to x squared plus 3xy plus y squared, right? Notice for this function given here, if we spend a moment just saying, well, what's f of x plus h comma y going to equal? Well, f of x plus h comma y would just go in, and everywhere we see the value of x, here and here, replace these two values of x with that quantity x plus h. And we see that initializing here for the value of f of x plus h comma y. Implying then, if we arrange this into the argument f of x plus h minus f of x comma y all divided by h, or sorry, and I'm missing my y here. I just see that. All right, all divided by h, this is going to equal this quantity seen over here. F of x plus h comma y is going to be this quantity. All right. That gets substituted in. We're going to expand that out here in a moment. I could have expanded back here if I desired. Minus, what is f of x comma y? This is just f of x comma y, respectively. Where when we expand this quantity, that will expand into this. X plus h squared becomes x squared plus 2xh plus h squared. All right, that's x plus h squared. 3 times x plus h times y becomes 3xy plus 3hy. All right, and then we add on to that at the very end plus y squared. Minus this quantity where the minus does have to distribute across the terms. And note that distribution of that minus across those terms. Where you do see some things that conveniently cancel. For instance, the x squareds will cancel. Right? The y squareds will cancel. And the quantity 3xy will cancel. Some terms of f of x plus h comma y will cancel with each of the terms in f of x comma y. And all of the terms in f of x comma y we will actually see cancel away. And that feels familiar if you remember doing this back in Calculus 1. Right? Or what are we left with? Well, we're left with 2xh plus h squared plus 3hy. We're really only going to be left with the terms involving h. Notice this doesn't involve anything involving h, so you're not going to subtract any of the h terms. Where that's convenient, having everything involving h remain, because we can now divide out at least one of those h's in each term with the h in the denominator. Leaving you with this first term, 2x, plus just h for the middle term, plus 3y for the last third term when you cancel that h. Now, what is this? This is the argument of our limit. The limit is h heads to 0. So if we take that argument and we just consider evaluating our limit now, right, we can see by definition f of x comma y, right, or I should say f's first partial with respect to x at x comma y is equal to the limit as h heads to 0 for f of x plus h minus f of x comma y divided by h, where we just calculated this argument above here to be the quantity 2x plus h plus 3y. Where the limit as h heads to 0 for 2x plus h plus 3y is only a limit that's interested in the value of h changing. 2x and 3y are constant in value. If we apply a little substitution method, just substituting in 0 for h, we can see what remains is just 2x plus 3y. And that is the first partial of our function with respect to x. All right, I do think I make note of that here. Yeah. So for our multivariable function, f of x comma y equal to x squared plus 3xy plus y squared, the first partial of f with respect to x is described by 2x plus 3y. Now you can start to read the following note. says, note the results of the calculation for this partial of f using the definition correspond to the derivative calculation of f with respect to x, treating y as a constant value. Right? Notice this result that we obtained by applying the definition, which involved that limit and developing the argument of that limit that we just did above, could have been found by just considering applying our derivative operator with respect to x, right, to this function seen here, treating the y's as if they were constant. Distributing the derivative operator here, distributing the derivative operator here, and distributing the derivative operator here, all with respect to x. Right? But we would be doing that with what we call partial derivative notation. However, interpreting it similar to the rules, well, using the rules that we already understand for differentiation. Note, using notation and the fundamental rules of differentiation, substituting the partial derivative notation dx in place of d dx, right, or I should really say del dx, del x in place of d dx notation. F's first partial with respect to x at x comma y would just have the first partial derivative operation with respect to x applied to it. Del x operator applied to it. So if we apply the del x operator to our function f of x comma y, that would be applied to x squared plus 3xy plus y squared. It would distribute itself across each term, x squared, 3xy, y squared, where you can notice in this line, I'm treating the y's as a constant multiple, and I am factoring the constant multiples out of each of those operations of the partial derivative operator. Now, this has no constant multiple in it. We're going to apply that operator rather directly. But when we apply it here to this middle term, when it distributes here, 3 and y are constant multiples, and they're going to factor themselves out using constant multiple rules of derivatives. Similarly, when it applies to the last term, y squared is a constant multiple, and if I want to, I can factor that out and say what I really have here is just the derivative with respect to x for 1, or the partial derivative with respect to 1, of x with respect to 1. Sorry, the partial derivative of 1 with respect to x. Let me get that right. I'm trying to get that partial in there. All right. But I get mixed around, folks, because the calculation is no different than what we did back in Calc 1. To calculate this partial with respect to x for x squared, we just calculate the derivative with respect to x for x squared. That is just 2x, as we understand it back from Calc 1. To calculate this partial with respect to x for just x, right? It is just the derivative with respect to x for that x. The 3y has been treated like a constant multiple and factored out of the calculation and doesn't have to be considered. Treat the y like a constant. And it's back to Calc 1. Right? Where we know the derivative with respect to x for just x is 1. So we get 3y times 1. That constant times 1. Right? Plus, here we're going to have y squared times the derivative of the constant 1. And we could have left y squared in there too and just said all we have here is the derivative with respect to a constant. And what is the derivative with respect to just some constant? Well, that is 0. So really in this last term, y squared times 0, or the derivative of what would just been the constant at the end of this term, or the constant term at the end of this function, would have all just resulted in 0 in the end anyway. We see it go away here. This is all just a plus 0 at the end. So it's not shown. Right? Coming from that constant term at the end of this function, constant with respect to the fact that we're only looking at partials for the case of variable x. Right? Simplifying this statement, you do just get 2x plus 3y. Right? And that is what we calculated above using the defined value for that first partial. Right? That 2x plus 3y was this result we calculated right here, given above. Right? Except here, we used some of our fundamental understanding of derivatives, or derivative rules from chapter 1, from our study of derivatives. Don't date yourself with chapters, Fred, right? So, we can just apply those rules from our study of derivatives, treating the y as a constant, and calculate partials in the manner I illustrate here. All right? Now, I do have a few more examples to get into while taking these ideas just a little further. As with derivatives that we studied back in Calculus 1, we learned that the derivative operation just applied once to a function was known as the first derivative, but itself was a description of functional behavior. Functional behavior also dependent upon its independent values. All right? We can take an analogous to that in our case of what? Partial derivatives, folks. The partial derivatives, f with respect to x, the partial of f with respect to x, and the partial of f with respect to y, are also known as the first partials of f. Right? They are the first partials of your function z equal to f of x comma y. Right? And in addition to the first partials of f, there does exist what we call second partials of f, denoted and interpreted as follows, right? You do have your second partials of f with respect to x, which we might see here given with this notation, and we could also incorporate the z into all this. Z could have a double subscript x, right? This would be our second partial with respect to x, and it's denoted not with a double prime, because prime notation doesn't work for us here. We see this double subscript x. And that means we just take the partial with respect to x twice on our calculation. Right? It's just going to be applied twice on our multivariable function. Once to obtain the first partial, and then applied again on the first partial to obtain the second. And we see something similar with respect to y. Your second partial of z equal to f of xy is zyy, right? Z sub yy, which is f sub yy's of x comma y. It's f's second partial with respect to y, right, at x comma y. And that is just taking two partial derivatives with respect to y. Right? So there is that analogous that we do have what are called higher order partial derivatives, the second partials. Right? And the second partials are going to be useful to us, folks. We're going to be using them actually in a study of max and mins on these surfaces. Partials are going to play a role. Second partials. As well as there is a case that isn't really analogous, but comes about because we do have two independent variables now. And that is what's called the mixed partial. The mixed partial is an example, or a unique case of what's known as a second partial derivative. You are taking a derivative twice on a function, but not twice with respect to the same variable. You're taking it twice with respect to two different variables, the two independent variables on our function x, and then y, or y and then x, right? And that's known as the mixed partial, right? it is highlighted this way. Right? Which does mean take the partial with respect to x first and then y. Technically. But one thing we do point out is that mixed partials, regardless of order, are always equivalent. Right? Note, for the mixed partial, order of the partial differentiation does not change the result. Notice, the partial with respect to x first and then y is the same thing as taking the partial of y first and then x. So the mixed partial written this way is really equivalent to the mixed partial written this way. Right? There is some mixed partial equality that happens with functions. Uniquely, right? You're going to say, well, that's unusual, and that is. That's unique. That always happens. For any function, if you find its partial with respect to x and then find it with respect to y, you get the exact same description if you first found it with respect to y and then found it with respect to x. Yeah, it's called the equality of mixed partials, folks. Take note. I think another example on all this. Consider the second and mixed partials for this function. F of x comma y equal to x squared plus cosine x sine y. All right. If you want to practice ahead in these, folks, I always try to give you an opportunity to pause the video and maybe try your hand at that. But what we would note here is that f's second partial with respect to x, right, would just be applying the second partial operator to our function, multivariable function, which is just going to apply the operation of the first partial with respect to x twice. Right? First on the function and then second on the result of the first partial applied to that function. Right? When we apply this first with respect to x, it distributes across the terms. And when it's applied to this first term, y squared is a constant. X's partial, or x's derivative with respect to x is just 1. So it's that constant times 1, and it becomes y squared in value. When it distributes itself as an operator to the cosine x sine y, the sine of y will be a constant. It'll factor itself out of that operator. And the operator will only apply to the cosine of x. Derivative of cosine x with respect to x, negative sine x. So we see down below here negative sine x sine y is our result. Now if we apply that operator again with respect to x, a second round on the result from the first, right, it will again distribute across these terms. Some are different, rule of derivatives. When it applies itself to just y squared, now y squared is a constant. So the derivative with respect to x of a constant is 0. So that is 0 out in front here, but we don't usually show nothing. Right? So it's really just minus whatever follows. And that's going to be the derivative of the sine x sine y. Now, that derivative operator, again, will only apply itself to the sine x. The sine y will be treated like a constant. It'll factor itself out. The derivative of sine x we know is cosine x. So in the end, you're going to be left with negative derivative sine x times sine y, or negative cosine x sine y in value. That would be our second partial with respect to x. You would have to perform 2 iterations of the partial derivative with respect to x on our function. First on our function, second on its result of the first application. All right. We could do this similarly with respect to y. Now you'll notice this time around, when it applies itself with respect to y the first time, xy squared, x is a constant, y squared's derivative with respect to y is 2y. So it'll be 2y times that constant of x, which would be 2xy. When it distributes itself to the cosine x sine y, the cosine x is a constant, sine y is where it applies. The derivative of sine y is cosine y. So it's going to be cosine x cosine y. Cosine x is a constant in its application. Now when we apply it in a second round to this statement here, when it applies itself to 2xy, the 2x is a constant, so it just applies itself to y, and the derivative with respect to y for y is just 1. So this is technically 2x times 1, but we write that as 2x, plus what the derivative would be when we apply it here. Again, now it's going to only apply again to cosine y, which is negative sine y. So that plus cosine x times the derivative of cosine y becomes negative cosine x sine y in value. And that becomes my second partial with respect to y. This is my second partial with respect to x. That's my second partial with respect to y for my multivariable function f of x comma y, seen up above here. Treat the variable not of interest in the partial derivative calculation as a constant. Whereas for the mixed partial calculation, right, we know that if we take the first partial with respect to x on xy squared plus cosine x sine y, we explained above that that results in y squared minus sine x sine y. Or now if I take that results partial with respect to y, we haven't seen this yet. When it applies to y squared, that's just 2y. But when it applies here to the sine x sine y, it applies to just the sine y and becomes cosine y. So this results partial would be negative sine x cosine y. That is what would be our mixed partial calculation. And remember what we said about mixed partials, it doesn't matter the order. Switching the order doesn't change the result. So I do highlight that here. Note the equality of mixed partials. First, with respect to y, we've explained above, was 2xy plus cosine x cosine y. That was in our second partial with respect to y calculation. That was what we got first round of that. But now if we took that and found its partial with respect to x, the 2y is treated like a constant multiple. The derivative of x with respect to x is just 1, so that's 2y times 1, very similar to above. But you get 2y. Plus the derivative of cosine x cosine y. Cosine y is a constant. Derivative with respect to x of cosine x is negative sine x. So you get negative sine x times that constant cosine y. Negative sine x cosine y. 2y minus sine x cosine y is that mixed partial. And notice the equality here, folks, regardless of the order that we take those two partials in, changing the variable each time. They get the same result. It's called the equality of mixed partials. All right. Now, I have one more example to give you here. It's a little overbearing, but these do get trickier. You may also have to mix in some product rule. You may have to mix in some quotient rule. You may have to mix in some chain rule of your single variable calculus. All right. However, with the introduction to multivariable functions, we're going to replace these techniques in the following section with what's called the chain rules for multivariable functions. So even though these look a little overbearing, folks, we're going to develop some rules that are going to help us calculate through something like this a little quicker in the next section. All right? By introducing multivariable functions, we can upstep our rules of differentiation into what we call the chain rules for multivariable functions. There's essentially just a collection of chain rules that really describes all of our advanced rules, like product rule, quotient rule, or chain rule for single variable calculus. All right. Consider finding the first partial, and we'll just do one here because this is rather lengthy, you're going to see. But let's say if we wanted to find the first partial of z with respect to x, and z was this multivariable function, 4xy e to the x squared y, all divided by x minus y, where we have this factor 4xy times this factor e raised to the power of x squared times y, with that product all divided by x minus y in value. right? We certainly might see here we have a mix of several rules. With the fractional form, that certainly is a little quotient rule going to play a role here. With this product in the numerator, yeah, there's going to be some product rule. And with the approach of that product rule, trying to calculate something like the e to the x squared times y's derivative might require a little chain rule. Or likewise elsewhere in our calculation might require some chain rule. Right? Depending on how we approach this calculation, folks. All right? Because keep in mind, you could also rewrite it the negative one in there. You could write it as this. You could express your function this way and ditch the quotient rule for some mix-up and chain rule here. All right, involving a little product and chain rule. Additional product and chain rule. So there's different approaches that are kind of analogous to our single variable calculus and the derivative calculations. Right? That we're going to approach with, or we could start to approach with some of our understanding of single variable calculus. All right? Here I go with the quotient rule. Here I do go with kind of what I see. I do see that quotient first. All right, I do take note that all these rules kind of mix up in this one problem. So beginning with the quotient rule, we might begin to conclude that what we have here for the partial with respect to x is just going to be, now I always like to start in the denominator. It's always going to be the denominator of the function squared in its result, x minus y squared. And then I know once I start there, this denominator, x minus y, is actually where I start the numerator too. It's going to be x minus y times the derivative of my numerator. You see that here. It says x minus y denominator times derivative of my numerator. That's this. Minus my numerator. You can see that's my numerator times the derivative of my denominator. Now, those aren't full derivative calculations. Those are partial derivative calculations with respect to x in that quotient rule. But nonetheless, it's still quotient rule from single variable calculus. Everything is over your denominator squared, where in your numerator, you have your denominator times the derivative of your numerator minus your numerator times the derivative of your denominator. Right? So now what we really have is to simplify these two derivatives. This one back here shouldn't be too tricky. What's the partial with respect to x for x minus 1? Distribute across the terms. With respect to x, it's just 1. With respect to y, it's a constant. So partial of a constant with respect to x is 0. So really, this is just 1. As a result, it's this derivative that's going to be a little unbearing. But not undoable, right? It's going to be a little rigor. We're already into a little rigor here. But organize it, folks. Break it down. Work it part by part. All right? You can tackle those harder problems, right? Component by component, part by part, brick by brick. All right? So notice to begin with, I do take note of that quick partial here at the end. That's quickly 1 in value. But from product rule is what we're going to have to use here. All right? And the way I break up product rule, you'll notice, is I actually break right on the product right here. I could really get complex with my product rule, but I'm going to kind of keep it simple. I'm going to try to make it just one product rule here. If I think of it as 4xy as the first, I think I can tackle that product, that derivative with respect to x. That's 4y. That's going to play a role right here in my product rule. That'll be times by my second factor, e to the x squared y. plus my first factor times the derivative of the second. Now, e to the x squared y, there's really no way to break that into a product of two quantities. Well, there is, but nothing we want to get too heavy into in that exponential. Right? Notice that is e to the x squared times e to the y. No, raised to the yth power. So it's still some ugliness there. So let's go this route. Now, I do note that derivative with respect to x for 4xy, again, quickly is 4y. Treating the y like a constant, the derivative with respect to x. Treating the 4y as a constant, the derivative with respect to x is 1. As for the partial with respect to x for e to the x squared y, we're going to need to use a little chain rule. So its derivative of the interior would be the derivative of x squared y with respect to x. That's 2xy. Times the exterior function. The exterior function would be e to the u's derivative, which would be e to the u. But u is that quantity x squared y. And remember what this is down here. This is u prime, right? Or what we might say is the partial of u with respect to the partial of x. Okay. But if we let u equal x squared y, that partial is just 2xy. So we build our derivative 2xy e to the x squared y here. Substituting those into the above result, this is our last example here, folks. We would have x minus y times this derivative minus this factor times the derivative that resulted in 1. Right? That is equal to this as we start to expand what was inside the brackets to obtain this. We then will combine these two, take the product of these using a little what? A minus b, a plus b form. That will result in that result. Where if we subtract this, notice we do have some like term there. 4xy e to the x squared y is subtracted from 4xy e to the x squared y. So we're really left with just these three middle terms. Right. Where we can factor that, we could factor a 4y squared e to the x squared y out of that and be left with the trinomial form 2x cubed minus 1 minus 2x squared y. All over just that x minus y squared. This value we see down here. This is that partial. Right? We might say here, just to finish it, because we are done. I don't have much beyond this. Thus, z's, not that. Z's partial with respect to x is equal to this result. This is one way to express that result, folks. Right? Certainly, you could see this expressed a lot of different ways. Remember, this is describing a rate of change on that surface with respect to only x being allowed to change on that surface. So regardless of what form it looks like equationally, if you were to look at it at a given point, some xy coordinate in space, thinking of it as being also some function f, well, f's first partial with respect to x at x comma y, right? You'd be able to look at it at any given value of x equal to a and y equal to b. You could substitute a and b into this form for x and y everywhere you encounter a. Well, everywhere you encounter x and everywhere you encounter b. Right. So regardless of the form in the end, if you were asked to evaluate it at any point, it would evaluate to the same value, describing the rate of change in the output of that function, in this case with respect to only the variable x being allowed to change, at that coordinate where x would equal a and y would equal b. All right. Substituting in that a and b would give you that value seen here. All right. That's partials, folks. That's partial calculations. I did go through a rather heavy calculation at the end just to show you that you can break these down bit by bits. The strategy is similar to what you did back in Calculus 1, though. You will just be taking derivatives, treating the variable not of interest in your derivative, taking derivatives with respect to just one of the variables, treating the other variable like a constant in our calculation. All right. You can do this for x, and you can do this for y when you have that function f of x comma y. All right. Just trying to scroll up here, and in case you missed anything in the notes, be able to go back and get that real quick. Pause the video. All right. As we kind of recount our lesson here. In the end, what we are describing is how quickly is z changing the output as we pass through this point either along this path or this path on our surface. What we're going to see is these two calculations are going to later be able to be used to calculate the rate of change in z with respect to passing through this point at any path. That's going to be known as a directional derivative. And we're also going to use those to calculate tangent planes, folks. Right? All this goes back to some fundamental definition. Right? Some fundamental definition that does apply the use of limits, because remember, calculus is the study of limits, folks. So here's our limits connection, where we are, again, also making connection to ideas that we are familiar with in our study of derivatives from Calculus 1. All right. I know this lecture is kind of a long lecture. I was hoping for the 45-minute mark, and I'm a half hour over that. So I don't know what to say about that, folks. But I did give you a thorough study here of partial derivatives. You can always, well, I always say this after the fact because I never know how long the videos are going to take. But keep that in mind as you watch future videos, as you see those timelines. You can always pause. And I do try to break up my videos where you can see some of its theory, put that horizontal line in there, right? So you kind of know where a pause is coming if you're following along in the notes at home. Right, where you can certainly pause the video and go back and rewatch sections if necessary. Right, and I hope you're doing some of that at home. Hope you're watching those videos out there, folks. I am putting these together for you. Sometimes the book is not enough. Sometimes the book is too much. Sometimes even. Right, my goal is to try to break this down and make it as simple as I can. Keep it simple. I don't know. Right? Subliminal. All right, folks. I hope you're all doing well out there. I'll get this video up and posted. I do want to do a demo for you. I do a little beginnings of multivariable functions on Mathematica. I tried something yesterday and I just did not like it. I'm not going to post that video. I'm going to go back. It's too tricky. It's too tricky, and I'll explain all that when I get into it. But I'll end this one here. Hope you're all doing well. And I'll see you in class. See you then.